Everybody on screen?
Yes.
Can y'all hear me okay?
Yes, sir.
All right. So today we're going to start this topic dealing with pKa and acidity. And so I'm just going to give you basically an outline of what we're going to talk about between today and Friday. It may extend into Monday. It just depends on how much we actually get through. So we're going to learn the difference in Ka and pKa, which we'll do in a minute, how to calculate pKa, and then how to determine what's called like the relative acidity if you're comparing two acids, determining how much more or less acidic one acid is than the other. We'll talk about that. And then we'll talk about the factors that dictate pKa, and then predicting acid-base equilibrium. That's a very easy concept. We're actually going to do that before we do some of the other stuff. And then determining acidity based on conjugate base stability. So that's really the crux of the discussion is going to be about that. So if you watch the video, you have, and we're talking about Bronsted acids, right? So these are H plus donors. And then Bronsted bases, you should remember this from G-Chem, are H plus acceptors. Right, there's another type of acid-base relationship, and that deals with what we call Lewis acids. Right, and a Lewis acid is an electron pair acceptor. And then a Lewis base, that's an electron pair donor. Right, so we're going to talk about, we're going to center our discussion around Bronsted acids and bases. So let's go back and let's look at a simple Bronsted acid base. Let me add a page in here. Right. So let's look at just a simple acid base. And let me use a real acid. And a real base. Right? So this is a really simple acid-base reaction. This is my acid, and then this is my base. It's a Bronsted acid because it has an H plus that it can donate. And then my base is a Bronsted base because it has a group on it that can accept H plus. Right? So here, this thing is going to react. Right? And so I'm going to end up with Na plus, let me put some electrons around bromine, and then Br minus, right? And then plus H OH. Y'all following that? So HBr plus NaOH, this is my acid, this is my base. And then over here, this is what we call the conjugate acid. And then this is what we call the conjugate base. All right. Everything that we talk about from this point forward is going to be based on the conjugate base stability, right? So Br is the part of the conjugate base that we care about. That's going to determine how well HBr loses H plus, right? So the conjugate base is going to really dictate how fast H plus comes off or is removed. Right? As a rule of thumb, if the conjugate base is very stable, H plus is going to come off fast. If the conjugate base is not very stable, then H plus doesn't come off as fast. So I'm going to write that down too. And I'm going to abbreviate conjugate base as just CB. Need to add another page. Pages get out of sync. All right. So let me go back to here. So H plus is lost faster if the conjugate base is stable, right? And vice versa. It's lost slower if the conjugate base is unstable. All right. Any questions so far? So in an acid-base reaction, you got an acid and a base, and that's going to give rise to a conjugate acid and a conjugate base. What, based on what you see here in this example, what's the conjugate base? Where does it come from? Anybody? No, speak out at once now. So let's put some arrows in and see if we can figure this thing out. Y'all quiet today. It's a holiday. Still Labor Day. All right, so we have HBr plus Na plus OH minus. Right, so this is the way that this works. Let me show you how this works. So the base is going to attack here at the proton. The reason is because there's a dipole in this direction. That's partially positive, that's partially negative. All of your reactions that happen because of these dipoles. Anytime you react an acid with a base or a nucleophile with an electrophile, it's all going to be based on dipoles and polarity. Right? So when that happens, I also have to break the HBr bond and give those electrons to bromine. Right? So on the other side of the reaction, I'm going to draw it this way. I'll have HOH plus Na plus and then Br minus. So we said this is the conjugate base. What's the conjugate base's relationship to the base? What did the base do to become the conjugate base?
It gave off electrons.
Mm-hmm. Gave up a pair of electrons, that's true. And in doing that, what else did it do? It also picked up H plus, didn't it?
Yeah.
So the conjugate base is the base plus a hydrogen. Are you following that?
Yes.
I'm sorry. This should be conjugate acid, my bad. The conjugate acid is the base plus a hydrogen. And then what about the conjugate base? What's the relationship between the conjugate base and the acid? Is it the acid minus a hydrogen?
Yeah.
Yeah. So the conjugate acid is the base plus H plus, and the conjugate base is the acid minus H plus. Is that making sense? This is the basis for everything that we're gonna be doing. So if you're following this, the rest of it is gonna be very easy to follow, right? So we need to be able to identify conjugate acid, conjugate base, and then acid and base. All right, are we okay so far?
Yes, sir.
All right, so how do we measure? Let me go ahead and add a page because I already know I'm gonna run out of room. All right, so how do we measure acidity? I'm gonna come back to the conjugate acid, conjugate base stuff in a second. How did you measure acidity in part one? What did you use? Anybody remember? It was an equilibrium reaction, right? Where you had an acid, HA, dissociating into H plus A minus. Do y'all remember that?
Yeah.
How did you determine how acidic HA was? Do you remember? Was it Ka?
Yeah.
So H plus A minus over HA, the concentration. Is that right?
Yeah.
And so for a strong acid, was Ka high or low? Right? It's a big, Ka is a big number for a strong acid. Are you following? And this is measuring basically when you add an acid to water and it dissociates completely or almost completely. Right? So for a strong acid, you have a high Ka, and this is fully dissociated. So fully broken up. Right? Fully dissociated. What is that? So let's think about this in terms of that reaction. If HA is fully dissociated, or 90, let's say 99% dissociated into H plus and A minus, what's the concentration of HA in that equation? Right here. Is it going to be a large number or a small number?
Small.
It's going to be a small number. If this breaks up into its components, there's not going to be much of it left, right? When it dissociates. So when you put it in that Ka equation, the HA, the number is small. That means that the overall value of Ka is going to be big. That's why for a strong acid, there's very little HA left. So Ka is a big number, right? Because you're dividing the concentration of H plus and A minus by a very small number. Are y'all following that? So for a strong acid, Ka is high. What about for a weak acid? What can we say? Can we make the reverse argument?
Yes.
We can make the reverse argument, right? Ka is a small number, and it's only partially dissociated. Uh-oh, sorry about that. Partially dissociated. Right? What does that mean for HA if it's only partially dissociated? That number gets a little bigger, doesn't it? In the denominator.
Yeah.
Yeah. So that means Ka is going to get smaller as there's more and more HA left over. Right? So when we talk about acidity and Ka, that's normally used for acids that dissociate readily, right? But in organic, you don't have acids that readily dissociate like that unless they are super, super acidic. That's sort of the reason why we use Pka in organic is because We use that for acids that don't readily dissociate. Right? So we use a different measure for organic acids. We use pKa. And this is a lowercase p. Right? So all that is, if we want to measure the pKa, it's the negative log of Ka, or the log of 1 over Ka. All right, so the values are going to be different, right? Because if you have a negative log, that means that if you put a big number in for Ka, the pKa is going to be smaller, right? So for organic acids, right, you have a low pKa for strong acids. Sorry about that. Right, so strong acids have a low pKa. The lower the pKa, the stronger the acid. And then, let me add a page right quick. By the same token, for organic acids that have a high pKa, those are weak acids. Right, and as a rule of thumb, your pKa is based on the stability of the conjugate base. Right? However, whatever your conjugate base is, the more stable it is, then the more readily the acid is going to give up H+. That's what everything is going to be based on, that idea, that axiom. All right. Any questions so far?
No.
I have one.
Come on.
So pKa is only for the organic acids and bases,
Yes.
and Ka is for the regular acids and bases.
So Ka would be for mineral acids, like some of the acids that you would use in Chem, because when you add them to water, they dissociate readily, right?
Mhm.
So you use Ka for those type of mineral acids and inorganic acids, and then you use pKa for organic acids. I'm gonna show you like a bunch of different organic acids, and you'll understand why. Because some organic acids are not soluble in water, so you can't use Ka to measure them, not directly. So that's why you use something different. So you use pKa.
Okay.
Yeah, good question. Let's go to some examples. I'm gonna start at the back right here. Right, it says apply the arrows, but we're gonna do more than that. We're going to figure out which one is the acid, which one is the base. We're going to figure out what the conjugate base is. We're going to look up the pKa's, and then we're going to also determine the equilibrium, because determining equilibrium is not that difficult. And I think we can do all of that with these examples. All right. So in the top example, let me put some electrons on oxygen. And close this out. All right. So let me put some electrons here. You know, oxygen has 3 lone pairs and is negative. If you had to pick, and let me throw a sodium in here too, because I want you to get used to seeing these counter ions. If you had to pick, which one of those would you pick to be your acid? Right, and keep in mind what the definition of a Bronsted acid is. It is a what? Based on what we just said.
It's H+ donor.
It's an H+ donor. That's right. So which one of those of the two has a H+ that it can give away?
first one.
The first one. Now I know you're looking at the hydrogens on here, right? Saying, well, those you can give those away. Those are not acidic. The hydrogen attached to carbon versus hydrogen attached to oxygen is going to be totally different, right? Those those protons that are attached to carbon are not acidic at all. They actually have a pKa somewhere around 50. So very high pKa, very difficult to pull off without a super strong base. So you're not gonna touch those. So this is gonna be my acid, right? Which makes this by default my what? Base. Yeah.
Are you adding
Yeah, I added that
Okay.
in. I add that in so that we can get used to seeing, because under normal circumstances, that oxygen is not just going to be negative just floating around. It's always going to have a counter ion. Right? You'll always have a counter ion with oxygen. Any negative atom is going to always have some type of counter ion around it. All right?
Okay.
So now that's my base, that's my acid. On the other side, which one of those is the conjugate acid? And remember what we just said up top. The conjugate acid is what? The base plus what?
H.
Plus H, plus a proton. So which one of those on the right side, on this side, is the conjugate acid?
The first one.
This one. Good. That's my conjugate acid. And then by default, that makes this the what?
Base.
Conjugate base. And I'm going to take that sodium and stick it right there, because this is, and I'm going to put my electrons around oxygen here and put them over here too. All right, let me ask you a question from the last exam that we took. What type of, well, no, actually it won't be, it'll be on this upcoming exam. What type of attraction is that between sodium and oxygen? Is it covalent or is it ionic?
Ionic.
It's ionic. Very good. What's another name for that? What do we call it? We call it an electrostatic attraction, right? It's just a negatively charged atom and a positively charged atom hanging out together because they got different charges. Is that okay?
Mm-hmm.
All right, now let's do a little bit of arrow pushing here, because it asks you to supply the arrows. All right, here's the let me go down here in a blank space and kind of give you a generic version of this. If you watch the video, you saw it already, right? So my acid, this is my acid, and then this is my base. And this never changes. If you learn this, you don't have to learn anything new with respect to acids and bases. It's always going to be the same. The base is going to give up a pair of electrons to this proton, right? This is either going to be called deprotonation, or you can call it proton transfer. Both terms are interchangeable. Right? Whenever I attack the proton, the atom that is bonded to is always going to be more electronegative than it is. So I'm going to always have a second arrow giving those electrons in that bond back to that atom. Are you following? Let's get some basics out of the way. Why are we using a double-headed arrow? Somebody tell me that.
Those are transferring fluid.
Because it can go.
I want you to look at how many electrons are on that base.
2.
2. How many electrons does it take to make a bond between 2 atoms? A covalent bond. 2, right? Every bond is composed of 2 electrons. Is that right?
Mm-hmm.
Yeah.
Being shared. So the base is giving its pair of electrons to hydrogen, because hydrogen doesn't have any electrons. Once you break the HA bond, there's no electrons left for hydrogen. So the base is going to supply both electrons. Are we okay with that?
Yes.
All right. So once I attack hydrogen, I have to break that HA bond because number one, hydrogen can only make one bond. Number two, hydrogen doesn't really follow the octet rule because it only has one electron anyway. Right, so both electrons go back to A. Is that okay? So then I'm left with A minus plus the conjugate acid. So this is conjugate acid, this is conjugate base, this is acid, that's base. Is that all right? Let me sneak another term in here too. The term is heterogenic. That's how you make, that's how this bond is made. It's two electrons. Let me not try to squeeze that in there. I'll go underneath here. So this process is what we call heterogenic, right here. Right? It's how it's bond formation when one atom supplies both electrons. You're going to see this term again, but I think it's a good time to introduce it. All right, so this bond formation when one atom supplies both electrons. Can you see here that the base gave both of its electrons to hydrogen to make the bond that's over here? Yes or no?
Yes.
Yes.
All right. And then by the same token, you see how the HA bond breaks and both electrons go back to A? That's what we call heterolytic. We're going to call it cleavage. Right? So let me zoom in so I can write this with enough room. So this is bond breaking. And then one atom takes both electrons.
Dr. Russell,
Mm-hmm.
so that hydrogen on the conjugate acid, it wouldn't be a positive, or
No.
is it already a positive because
No,
it's added to the base?
No, it's neutral. If it was just by itself, it will be positive. But the fact that it's covalently bonded to whatever atom in the base picks it up, it's neutral.
Okay.
Yeah, good question. So heterogenic formation is when you make a bond between two atoms, but one atom supplies both electrons. Heterolytic cleavage, that's what we call a bond. When we break a bond, we say we're cleaving it. Heterolytic cleavage is bond breaking where one atom takes both electrons. So that's what happened here. Can you see that? You see how A picked up both electrons and now A is over here? Right? And the arrow from the bond between those two is pointed towards A. That means that A picks up both of those electrons. Is that okay?
Yes.
If you watched the video, then you saw the description. It's like HA are together, and then when the base comes in as the new partner, H decides to leave with the base, but the A is saying, no, well, you can leave, but I want my electrons back, right? You can't take them with you. So that's how, when that bond breaks, those electrons are always going to go back to the more electronegative atom, which is A in this case. And you got heterolytic cleavage and then heterogenic formation. All of this is happening in this proton transfer. Any questions?
No.
Right? Everybody feeling comfortable, even though it's real quiet. All right, so let's go back to here where it says supply the arrows. What are you going to do now? Right? We know what the base is. We know that the base is always going to be the supplier of electrons or the source of electrons. And then the acid is going to be the source of H plus. Yes?
Yes.
So how would you show, what arrow would you draw? How would you show the base interacting with the acid?
We would do the acid. We would do the acid to the conjugate base.
Okay, so.
And the base to the conjugate acid.
Okay, you're right. But what I'm trying to get you to tell me is what the mechanism is. How does it happen? Right? So how it happens is I'm going to take a pair of electrons from the base. Is that right?
Yes.
And I'm going to donate them to hydrogen. Yeah. This is the mechanism. That all that is. When you hear the word mechanism, it's just a step-by-step depiction of how a reaction happens, right? So the pair of electrons is going to come from oxygen. And then I'm going to break, I got to zoom in some, the OH bond and give those electrons to that oxygen. Following? And that never changes for acid-base reaction. The mechanism will always be the same, no matter what. Now, does that explain where the conjugate acid comes from? It does, right? Because this arrow right here is telling me that I'm making a bond between oxygen and hydrogen. And this arrow is telling me that I'm breaking the bond between oxygen and hydrogen. Yes or no?
Yes.
What type of bond formation is that again? It's
Heterogenic.
heterogenic. One atom supplying both electrons to a second atom to make a new bond, right? And then what type of bond cleavage is that going between H and O?
Heterolytic.
Heterolytic, right? One atom is taking both electrons from a bond between two atoms. All right. So that's the mechanism part, the arrow part, right? Now here's my conjugate acid and here's my conjugate base. I want somebody to look up, you can Google it real quick and tell me what the pKa of water is.
$15.7.
15.7, good. That was quick. You must be on that 5G. 15.7. Or we can round up. Normally you'll see it rounded up to 16. All right. Now I need somebody to look up the pKa of this acid, or what's really alcohol. It's cyclohexanol. Cyclohexanol. Right? I'll explain the name too, because I know somebody's thinking or getting ready to ask, why is it cyclo? How you know to say it, call it that? So we'll do that too.
It said about 18.
18? All right, I'm gonna take 18. I'm gonna take 18. All right. It's cyclo because you have one, let me count them out. One, not there. 1, 2, 3, 4, 5, 6 carbons. That's where the hex part comes from. The cyclo part comes from the fact that those 6 carbons are in a ring. And then the all part comes from the fact that the functional group here is what? Somebody help me out, because this is
alcohol.
It's an alcohol. So cyclo for the ring, hex, meaning the ring has 6 carbons in it, hexane, and then all is for the alcohol. We're okay so far?
Yes.
So we put the arrows in, we've drawn the conjugate acid and the conjugate base. Now the question is, which side is favored? Right? Let me put that. Let me give you a little snippet down here on predicting equilibrium. All right. So how do you predict equilibrium? I'm gonna give you the technical first, and then I'll give you the layman's explanation. Right. So the way to predict equilibrium is you always want to go from a stronger acid to a weak acid. Right? That's the direction you want to go in. So the technical way to say that is that the pKa of the acid should be lower than the pKa of the conjugate acid. So let me put this here, pKa of conjugate acid.
Dr. Russell.
Mm-hmm.
So when you try to see about equilibrium, like how you predict it,
Mm-hmm.
would it go to like the highest pKa acid?
Yep, that's exactly right.
But like how would you know, like just by looking at like the equation, like
Okay.
who has the highest pKa?
Good
Or
question.
would you have to like solve it?
No. You don't have to solve it. There's two ways to do it. One way is to look up the pKa, right? Or have it given to you. The other way is to compare the conjugate bases of the two acids. That's the more difficult way because we haven't talked about all the different factors that contribute to acid-base stability. So for now, we're gonna look the values up. All right.
Mm-hmm.
So you want to go from a strong acid to a weak acid, or a strong or low pKa to a higher pKa. Right? So the layman's term is to think of the reaction like a seesaw. Right? Everybody here has played on the playground, I'm sure. And if you ever was on a seesaw with somebody who was dirty, low down, and they jumped off, and yeah, you know the rest. Right? So the way that we think about this as a seesaw, let's say the pKa on the left side is 10 and the pKa on the right side is 50. Right? So the acid is 10, the conjugate acid is 50. Which way is that seesaw going to tilt? It should tilt toward the larger number, right? If you think about it in practical terms. Yes? Like if you got a person on a seesaw that weighs 300 pounds and on the other side you got a person that weighs 100 pounds, which side is that seesaw going to be tilted towards? Right?
The large side.
Right, you got a skinny person on the seesaw holding on to the little thing, like on the playground, and you got a real hefty person on the seesaw, right? They ain't holding on. They just whatever. They free. But that's what happens. That's what you expect, right?
Mm-hmm.
Right. So the seesaw, if I put the fulcrum here, the seesaw should be tilted towards the side with the higher pKa. That's the layman's way to think about it. So if you know the two numbers, it's always going to tilt towards the number that's large. Does that make sense?
Dr. Russell?
Yes.
So the stronger acids have a lower pKa?
Yes. Remember, because the pKa, let me go back up to here. Remember we said up here for organic acids, low pKa corresponds to strong acids. High pKa corresponds to weak acids.
Okay.
Right, because the pKa is the negative log of Ka. Right, so low pKa means that the Ka is actually a big number. Right.
Okay.
And we said Ka was, if it was big, that's for strong acids. If Ka is small, that's a weak acid. But the fact that it's a negative log, it's inverted. So it's negative log of Ka or the log of 1 over Ka. So an acid that has a low pKa is a really strong acid. acid with a high pKa is a weak acid. Got it?
Yeah, I got it now. Thank you.
Okay. Let's go back back to our example down here. So let's look at the top reaction. What do you think? If the pKa of water is 16 and the pKa of cyclohexanol is 18, which one of those is a better acid?
The cyclohexanol.
Think about what you're saying now. If by better acid, I mean more readily giving of its H plus. And that means that the pKa should be what? Lower or higher? Low pKa means that something is a better acid. Lower pKa. So of those two, which one has the lowest pKa?
The water.
Water. It's 15.7, right? So water is a better acid than cyclohexanol. You following?
Yes. So the lower the acid means that it's higher.
It's better.
Okay.
Lower the pKa, the better the acid. So when we predict an equilibrium, which side is going to be favored? The side where the pKa is higher. Equilibrium always favors the weaker acid, right? So which one of those two is the weaker acid?
Cyclohexanol.
Hexanol. So the equilibrium arrow is right here. I can draw them like this, where the large arrow goes to that side and the smaller arrow comes to that side. Right? Now let's think about it. I don't want to rush this. So let's think about why would the weaker acid be favored? Keep in mind it's an equilibrium. So you can go back and forth between the right side and the left side. Why is it that when you get to the weaker acid, it doesn't want to go back to the other side? Think about that.
Is it more stable?
Okay. Yes, it's less reactive, right? Which is another way of saying more stable. So the weaker acid is less reactive. Is that right? So does it give up H plus as readily as the water does?
No.
It doesn't. That's why when you make it, it's hard to go back to the other, go back in the other direction, because it's a worse acid. So it's not giving up H plus as readily. So you get stuck on the right side because that acid is not as good of an acid as water is. And that's what you want, right? In an acid-base equilibrium, you always want to go from a strong acid to a weaker acid. Is that okay?
Yes, sir.
Anybody not see it? Say something now. While we're in the preliminary stages. All right, let's do the same thing for the bottom reaction. I'm gonna rewrite it though, so I don't have to squeeze it in. Let me add another page right quick. Okay. All right. So let me look at it. Yeah. So let's take this reaction. We're going to do the same thing. We're going to label the acid, label the base, label the conjugate acid, label the conjugate base, put the arrows in, and then predict the equilibrium. So this is this plus this, and then I'm going to stick a sodium out here. And then oxygen is negative, sodium is positive. And then this is going to go to, again, it's acid-base reactions are always in equilibrium. The extent of the equilibrium is what matters, but it's always in equilibrium. So what's the conjugate? What's the acid? We get to do this without seeing the products. All right, so what's the acid?
The first one.
The sulfur, right? As a functional group, this is called what we call a thiol. Right, it's a thiol. Right, anytime you see a SH, it's like an analog of an alcohol, so we call it a thiol instead of an alcohol. It's a sulfur analog of an alcohol. All right, so that's my acid by default. This is my base. Is that right?
Yes.
Let me draw out the H2 because we got to put the arrows in. So where's my source of electrons going to be coming from for this proton transfer?
The base.
It's coming from the base, and specifically, it's coming from oxygen. Is that right?
Right.
So I'm going to draw the electrons from oxygen to here. Boom, like that. Now, what else do I have to do?
Break up that hydrogen and sulfur.
Break this. Let me put some electrons on sulfur too before I go further, because I want sulfur and oxygen are in the same group on the periodic table, so they got the same number of valence electrons, but the properties are a little different. So boom, we're doing that. Is that right?
Yes, sir.
All right. So what does the conjugate base look like, which is the acid minus a proton? Is that right?
Right. No. Yeah. No.
Is that right?
Yes.
That's
Yeah.
my conjugate base. Now, what does the conjugate acid look like? The conjugate acid is the base after it picks up a proton. Is that right?
Yes.
Right.
Yes.
So it's going to look like this, HO, like that. Yes or no?
Yes.
Yes.
That's my conjugate acid. That's my conjugate base. All right. I need somebody with some bandwidth, some 5G, to look up the pKa for 1, 2, 3, 4, butanol. This is butanol. But for 4 carbons, well, butan for 4 carbons, and then all because the functional group is alcohol. All right, so somebody look up the pKa for butanol. And we're gonna just stick it in, and we're gonna figure out which side of the reaction is favored.
Is it 16.95?
That's okay. I'll take that. That sounds about right.
Mm.
Right. So most of your alcohols will have most of your alcohols are gonna have pKa somewhere between 16 and 18. Right. That's a rule of thumb. All right. Let's look at let me see, 1, 2, 3, 4. Somebody look up the pKa for butane thiol. It should be a little bit, I think it should be less than butanol, but let's find out. Anybody got it yet?
10.2.
10.2. Look at that. Thank you. Who was that? So it's 10.2.
Amaya.
Thank you. All right. Now, the question is, now we're going to predict the equilibrium. So let's do it the layman way. We're going to put the seesaw in, right? The 10.2 is on the left side of the arrow, and the 17 is on the right side. I'm going to round it up to 17. Is that right?
Mm-hmm.
From a practical perspective, if you put those two numbers on a seesaw, the 17 is a bigger number, so the seesaw should tilt in this direction. Is that right?
Yes. Yes.
Right? You said 10.2. I didn't even finish. I was so excited that you found it. I didn't even put the 2 in. All right. So when we talk about predicting the equilibrium, which side is going to be favored? Is it going to be the reactant side or the product side?
The
Product.
reactant.
Active.
No, this is, let me,
The
Product.
Product.
yeah, let me help us out right here. This side, because I didn't write it horizontally. So I want to make sure we are all right. So this is the reactant. And then this is the products. Following?
Mm-hmm.
Yeah.
So the pKa of the acid is 10.2. The pKa of the conjugate acid is 17. Right? So keeping in mind, the reaction, equilibrium is always going to favor the weaker acid. The longer arrow should be coming this way. I'm going to change colors right quick. The longer arrow should be coming here. Yes?
Yes.
And then the shorter arrow should be going that way. Make sense?
Yes.
All right. So let me just recap what we've done. And then when we come back on Friday, we're going to do some more examples. And then we will have recitation tomorrow at 7. So, and we'll work, I'll pick a couple of problems to work more on this. Because I think it's not hard to grasp it. It's just going to take some reps. All right. So what have we done so far? We compared Ka and pKa. Is that right? We compared Ka to pKa. We've identified acids, conjugate acids, bases, and conjugate bases. Yes?
Yes.
We've defined Bronsted acids, and bases. Is that right? Define that. And then we also proposed an acid base mechanism. All right, we put the arrows in to show how the acid and the base interact with each other. And then the last thing we did was what?
Equilibrium.
Predict. Good. Acid, base, equilibrium. Right? We did a lot. But a lot of the topics are related. So when you have that kind of overlap, it's easier to cover those topics just looking at 1 or 2 examples. Right? So on Friday, we're going to do a little bit more. We're going to look at how to tell how many more times one acid is than the other. And we're going to do some more of these examples with the arrows, because I promise you, if you can push arrows, you can pass organic with no problem. But you got to practice pushing arrows, though.
Dr. Russell,
Yes.
can you go up a little bit?
Is that better?
No, like slide up, like go up.
Oh, back to here?
Yeah, 1 second.
Yeah, take your time. I'm gonna upload these notes to Blackboard too, so don't panic.
Okay. Thank you.
Mm-hmm. All right. Any questions about anything? Anything that we've talked about?
Dr. Russell, I have a question.
Go ahead.
It's not really about like the lesson. I just had a question about an assignment.
Uh-huh.
So for the one where it was like, what was it? One second, sorry. The FC groups and the IMF one?
Yeah.
Was that the assignment with the 1-1.34? Was that the one that was that?
No, the functional group, let me go to Blackboard, because I had a lot of issues with that. Not issues necessarily, but people turning the wrong thing in. So let me do this. Like, so because it was really the same handout. but it was just a different section of the handout that that was focused on. So let me pull it up.
Thank you.
And if you put the wrong thing in, and I'm not singling you out because of, you know, whoever, just shoot me an email and I'll clear it so you can put the right thing in. I'm not gonna not give you points because, I mean, we obviously did it in class, unless you want it in class and don't have it. That's different. So, wrong class. Teach too many classes. Much rather be on the beach in Jamaica. All right, so that was module 1A. Assignments. Let me share that. All right, so under assignments, so the functional group stuff, it was right here. It was this handout because we worked through a bunch of these problems, but they were all on different topics. But all the functional group stuff was down here, right here. All these problems that we went through and named all these functional groups, right? And then the water solubility and IMF, all that stuff was here. Boiling point, melting point, that was dealing with the intermolecular forces. But in all honesty, this wasn't even, sorry, it's like a C-130 flying over. This wasn't due. This won't be due until we take the test. So
And
really,
Dr. Russell,
yes.
you want us to do the questions we haven't done in class with you as well, right? Just complete the whole sheet for that assignment?
Yeah, only the ones that are highlighted though.
No, I'm talking about the one you just went over, like the Chem 320 in class assignment. You want us to do all the questions on there and the ones we went through in class, right?
So you mean, are you talking about here?
Yes.
Right now? Yeah. I actually told y'all to go ahead and finish these when we were looking at this, because we went through this whole handout, this whole part of the handout, to be honest with you.
Yeah, I'm talking about like the whole handout, because it's like 2 pages of that handout, right? Like that first page, and then you go down, you see it on the second page. Or you just want us to do that last page that says Chem 320 assignment?
All on the same. Can you see my screen?
Yes, I'm looking at it.
All right. So we did, when we were doing resonance, right, we did questions from up here. Right? We did a bunch of these questions, the highlighted questions. And then when we did, we also did a couple of the questions from here. I know we did here where it says add curved arrows, follow the curved arrows, and then draw a second resonance form. We did those 3, right? And then the other ones we skipped because that was dealing with isomers and we hadn't talked about that yet. So we left that out.
Okay.
And then we went to here, this was all our functional group stuff. Right, so the functional groups, we named all the functional groups up here. We did another thing where we pulled up, I think it was oleandrin. We did that, set that up for like an extra credit assignment. And then here, this stuff was from the first part, but you should be able to do it now because it's just putting in dipole moments and figuring out what the difference in electronegativity is for each.
Okay. One last question. So since we went over PKA today, do you want us to go ahead and start on that those PKA worksheets?
Yeah. So that's only what I did was, let me go back because I changed the worksheets, so it'll just be one big worksheet. So it's in here. It's in the second module. If you go down to assignments, you'll see. At first, it was like 2 worksheets, but I changed it. Because I combined a bunch of stuff to make it easier. So it's only one worksheet right here. Wrong. Clicked the wrong thing, my bad. Come on, little dinosaur. Right here. Right, so this is the handout that we were working on today. And we started out back here. not there.
And just do all the highlighted ones.
So this we did today,
Mm-hmm.
right? And then down here, we're going to work through. I'll tell you which ones we're going to do from here when we get to that point. And then this, we're going to work all of this, because this is actually less. It's not as bad as it looks. We're actually going to start out Friday with this page. And then up here, go ahead.
That's just due before the test, like.
Yeah. Well, actually, I'm actually probably will wait, and I'll tell you which pages that are due. But yeah, it'll be due like Sunday after you take the exam. But so we're not going to be finished with the handout. So
Okay.
it's kind of, you understand what I'm saying? You'll end up turning it in twice. So just hold tight on that. But up here, we're only gonna work like specific highlighted problems, right? So for now, what we're gonna focus on now is this page, which we just finished, this page, which we'll do Friday, and then we'll go and probably finish this page also on Friday. Because this is all, it looks like a lot, but it's really not.
Okay, thank you for clarifying.
Yeah, no problem. So when we get off, I'm going to host the recording, which I need to stop.